So first off, the binary mixture. So chloroform and n-Heptane are vital industrial chemicals, though they typically serve different commercial sections. Chloroform is considered a dense chlorinated solvent, which is widely used as a solvent in pharmaceutical and chemical manufacturing. It is also used as a laboratory extraction solvent. N-Heptane, on the other hand, it's a non-polar hydrocarbon solvent, mainly used in petroleum refining, adhesives and coatings, and also octane rating reference fuel. For the industrial significance and applications, the binary mixture of chloroform and N-Heptane typically arise in industrial waste streams or specific chemical formulation steps rather than being synthesized purposely as a commercial product. One application for it is the polymer fractionation and purification. The binary system in the synthesis is used in the processing of advanced biodegradable polymers. It serves as a classic solvent and solvent pair for the fractional precipitation of bacterial copolyesters such as PHHV. Another application for it would be the specialty chemical solvent plants. The binary mixture leverages the contrasting chemical properties of a polymer halogenated methane, such as chloroform, and a completely non-polar long-chain aliphatic alkane, such as n-Heptane. The blends of these two chemicals are deployed in specialty extraction industries, where a fine-tuned adjustable solvent polarity is mandatory to isolate the organic compounds from biological substrates or the reacting matrices. For the separation process review, unlike many polar-nonpolar systems, chloroform and n-Heptane do not form a homogeneous isotope at the atmospheric pressure. However, they form a highly non-ideal solution characterized by a pinched region in their vapor-liquid equilibrium curve. The relative volatility shrinks dramatically as the mixture becomes rich in chloroform, requiring an exceptionally high number of equilibrium stages if processed using standard fractional distillation. So one separation is the fractional convectional distillation, because there is no isotope barrier, convectional continuous fraction can achieve high purities. However, due to the tight boiling margin and system non-idealities, high reflux ratios and towers with 40 plus trays are the standard. Extracted distillation can be also used, but to minimize the heavy utility demands caused by high reflux ratios, and entrainers such as a heavy polar solvent or an ionic liquid can be introduced to artificially swell the relative volatility of the chloroform over n-Heptane, drastically cutting the energy costs. For a standard industrial scale conventional fractional distillation unit separating at an equally molar recovery stream, typically operating envelopes reflect the following. The feed composition is about 40% to 60% mole of chloroform. It usually varies based on the upstream chemical or the cleaning process layout. For the operating pressure, the top column is usually kept at atmospheric pressure to prevent the thermal degradation of the chloroform and eliminate the need for extensive vacuum or pressure-related shells, while the bottom column is usually kept around 105 to 120 kilopascals. The operating temperature is tightly managed at the top temperature aligns with the pure chloroform boiling point, which is around 61 to 65 degrees Celsius, while the reboiler runs close to the n-Heptane's boiling limit, which is around 95 to 100 degrees Celsius. The reflux ratio would be between 2.5 to 4.5, which is highly relative to the ideal systems due to the pinched VIE behavior at high chloroform concentrations.
This slide shows the general equation used for vapor-liquid equilibrium of VLE. This equation relates the liquid and vapor compositions at equilibrium and forms the basis of our flash calculations. Since the mixture is assumed to behave ideally, the general VLE equation can be simplified into Newton's law. This simplified equation is used throughout our calculations. The main assumptions used are that the mixture behaves ideally, the separation is assumed to be complete, and both activity and viscosity coefficients are equal to 1. These assumptions simplify the flash design calculations. The objective of this project is to determine the amount of liquid and vapor produced, as well as the liquid phase vapor phase compositions. The basis used is 1 kmol per hour of feed entering the flash column. This is the important equations used in our calculations, including the Antoine equation, bubble point pressure equation, and dew-point pressure equations. These equations help determine the phase behavior of the mixture. Next, we apply overall and component mass balance to the flash separator. These equations are used to determine the liquid and vapor flow rates as well as the composition of each phase. This equation is used to calculate the vapor fraction produced in the flash separator. Once the vapor fraction is known, the remaining unknown compositions can be determined. The K value represents the equilibrium relationship between the vapor and liquid phases. It is calculated using the saturation pressure and operating pressure and is an important parameter in the flash calculation. This slide shows the calculation of saturation pressure using the Antoine equation at 76.25 degrees Celsius. The results show that chloroform has a higher saturation pressure than n-Heptane, indicating that it is more volatile and tends to enter the vapor phase more easily.
Okay, next we calculate the K values. So here is the formula, but at first we use the P saturation over P formula. So for the K1 values, after the calculation we get 1.526, and for the K2 0.475. After that we can calculate the V and L values. There are two methods to calculate these values. One of it is trial and error method, and also iteration from Microsoft Excel to solve for V. So based on Excel we got the value of V is 0.001 kilomole per hour, and for the L we can just use the formula L plus V equals to 1, then 1 minus V equals to 0.9989 kilomole per hour. Okay, so this is the example from our Microsoft calculation. Okay, so we move to the calculation part for the bubble point pressure and dew point pressure. So for the bubble point pressure, you can calculate by using this given formula, which is P bubble equals to summation of X times P saturation. We assume that the feed conversion are 0.5 for each. So after calculating, you can get that the pressure of the bubble point is 106.105 kilopascal. So for the dew pressure calculation, we can use this formula, which is summation of 1 over summation of Y over P saturation. We also assume that the P conversion were the same, which is 0.5. So after calculating, we can get that the dew point pressure is 76.796 kilopascal. So for the P system, we assume 106.07 kilopascal, which is this value in between dew point and bubble point pressure. So this indicates that the separation process can be done. Okay, so next we calculate the X and Y value. So for the Y, we just use this given formula. For Y1, after calculating, we will get 0.76 to 6 kmol chloroform per kmol. For Y2, 0.2374 kmol n-Heptane per kmol. Then for the X value, we can calculate using Y over K formula. And for the X1, 0.4997 kmol chloroform per kmol. And for X2, we will get 0.5003 kmol n-Heptane per kmol. So after calculating this total value, we must check the validity of this value. Both of it must equals total to 1, and after our calculation, we get both of it equals to 1, which is valid. Okay, so this is our TXY diagram for chloroform and n-Heptane at 106.07 kilopascal of pressure. 2 points of both end indicates the saturation temperature for both of these substance. And there are also divided 3 regions in this graph, which is the first region is liquid region, second is the two-phase region, which is suitable for doing flash separation process, and for the third region is vapor region. Okay, so for this diagram shows that the case for overall composition of 0.5 chloroform and heptane at 0.5 at 106.07 kilopascal. You can know that the suitable range of temperature which allow the separation process can be done is 76.2 degrees C until 85.4 degrees C. So this is the PXY diagram for chloroform and heptane at temperature 76.35 degrees C. They are also separated by 3 regions, which is the liquid region, two-phase region, and also the vapor region. Okay, so next this diagram shows case for overall composition of 0.5 chloroform and 0.5 n-Heptane at 76.25 degrees C. So the range of suitable pressure which allowed separation process is 76.8 kilopascal until 106.5 kilopascal. Okay, moving on to the conclusion. For overall process, which is the flash separation process, we can conclude that we assume our basis is 1 kmol per hour of equimolar mixture of chloroform and n-Heptane into the flash column. The operating system pressure is 106.07 kilopascal and operating system temperature is 76.25 degrees C. Initial feed composition for Z1 and Z2 are 0.5. Moles of liquid we calculate got 0.0011 kilomole per hour. Moles of vapor 0.9989 kilomole per hour. And for the liquid phase for X1, we get 0.4997 kilomole chloroform per kilomole. For X2, 0.5003 kilomole n-Heptane per kilomole. And for the vapor phase for Y1 equals to 0.7626 kilomole chloroform per kmol. And for Y2, 0.2374 kilomole n-Heptane per kilomole.